Yes, Hamza. Hello, dengar? You hear my voice?
Yes, madam.
Alright. Okay. Content. Okay. Right, we will start with lab 10, arithmetic and logic operation. Last time we do the load word, right? So, yeah. Okay, so last time someone asked about the load word and store word if they don't want to use the LUI instead of using the name of the variable here. Okay, so there's one of the student who gave me the coding like that. So there's another style of you don't want to use the LUI command, right? So last time I teach you to use this LUI register as 0 and then 0x1001. So here shows that address 0x10010000 is in E0. Sorry, is in S0, right? So like that. So then you can use your load word and then register T0, comma, register S0, like that. Okay, so that's the one that I have teach you last time. Okay, there's another style that one of the students asked me. They want to use like this, and then load word and then T0 and then X, and then ADDI, and register T1. Okay, just to see what are the values inside the registers. Okay, so register T0, and then we want to add 100 like that, and then store word. Okay, but when we want to use the store word, okay, when we want to use the store word, T1, and then they are using Y like that, so they want to store on another space. So okay. So now when we try to run the coding there like that, so what happened is that, okay, step, sorry, should be in hexadecimal, okay? So step, now, when you load the coding, okay, when I use the load word T0 and X, okay, so what happened is that there are two codings that would be generate or assemble. So in this case, what is X? What is X? X is data, okay, with the memory address. So what happened is that they load upper immediate of the address of X to register 1. So if I sidestep, now register 1 will contain the memory address. And then I would run ADDI and then add 100 on 100 on register 9. Register 9. And then so okay, so when I load word, it is 1. Okay, X is equal to 1. So 1 is loaded to register 8. And then add with 100. Add with 100. So you will get a result in register 9. Okay, not 65, 64, sorry. So 64 plus 1, the result is 65. 65 would be stored to to y. In this case, is another word here. So this is the value there that will be replaced. Okay, so that is the one that they gave me the answers for that. But okay, that is for example, if you want to save it on that space or maybe on another variables. Okay, so it also can be done like that. But what I want you to do is that if you are using it like this, which means that there is no other variables that you want to save it. Okay, but then when you want to store, usually you don't have an option and then you will save it back on the same position. But if you want to manipulate the data and then you want to save it on the next offset, you cannot use for like that. Okay, so it will give you error. It will give you error because what they expect on this bracket is that a register. Okay, register that point to the data here 1001,000. But if you are using a load word and then you point X, okay, you point X means that you just want to load the data on that variables. Okay, what happened is that they need a base register. So the base register is stored at the R1. And when I said, I did mention to you before on week 7, R1 here or 80 is a kernel register, which we not use. We cannot use on our coding. Okay, it will give you error. Okay, so it's only used for temporarily for the kernel. So in this case, they are storing it at the moment. And then after that, we cannot do the operation there. Okay, you cannot use the register 1 and then with an offset because I've done that and then it will give you error. I don't know why. So what you can do is that you don't have to put the load word there for the name of the variable. Instead, use the load address. If you don't remember what are the address there, let's say you have an input and then with the data word ASCII Z and then please input positive number. So positive number. And then when you have a value there, okay, so there's another integer that have a value x is equal to 1 like that. So it means that you don't know the memory address. So what you can do is that you just point the name of that variable. So point it to register as 0. So point the address of x to S0. So here you can use the variable name x. Okay, so x, the memory address of x, okay, will be stored into the S0 using the command load address. Then you can just use the offset and then register S0. Here, then you can use the next offset to be stored at. Okay, so then you can just use the whatever you can manipulate actually using the offset. So in this case, using the load address is much better rather than you just use the load word and then point the name of the variable to the registers. Okay, that is if in the case, let's say you want to store like a constant. Constant for example, the size of an array. So size is equal to like this and then word 50. Then you are only using a one time, so you want to load it into the registers. So what you do is that load word and then register T1 comma size, then you can use it. If there is a manipulation, means that you want to manipulate the data, means that is a data, not a size. Then you cannot, it's not suitable to use that. Okay, so there are two ways. One is that you are using the name of the variable and then load the data. The 50 here will be loaded into T1. Okay, but you cannot manipulate after that. Okay, when you want to do the store word, you can only store back on the same on the same variable, okay, on the same memory address. But if you want to do a manipulation like an array, then it's better to point an address. Point an address to a register to become a base register. That one is much better. Okay, so that's for the last time punya, not an answer, an option. Okay, if you gave that kind of answer, it is better to use load address rather than use the variable and then put it inside the load word. Not good. Okay, not a good practice. Okay. So now let me continue for the left hand. Right, so for this lab, we are going to learn about arithmetic and logic instruction set group, and then you would write a complete program using arithmetic and logic instruction set. Okay, so all the arithmetic operation in MIPS use R-type instruction format to perform their operation. Actually, they are all the arithmetic operation you will always use the R-type, except that we have a constant. Okay, let's say we have a constant. Usually what you write on your coding, you would initialize, remember, on your coding C++, right? Integer x is equal to 1. And then float, like that, right? Don't want to use the float. Okay, we are going to learn about only the digital number, okay? So, integer x is equal to 1. And then size is equal to 50, like that, right? So, these numbers is what we call as a constant, okay? So, this is our constant. So, small constants are used frequently and made up of 50% of operands, okay? Because of all the operation that we have done. Let's say if x is more than 0. X is more than 0. More than 0. This is also a constant. And then you want to do some operation after the if condition. So you want to put x plus plus, like that. So this is in C++ also can be written as x is equal to x plus 1. Okay, another constant. Okay, so there's a lot of constants run in the arithmetic and logic operation. Okay, so there are 3 ways of specifying constant in MIPS program. Okay, first is that using store them in memory and then load them. Okay, like what you have written in the initialization. Integer x is equal to 1, comma size is equal to 50, like that. So you can also write it like that, dot data, and then x is equal to word 1, and then size is equal to word 50. Okay, so like you store it and then you load back. Okay, you would load back. So in this case, first is I load the x data. And then second is that I would load word like this, T1. And then because I just want to use one time only the size, so I would just load the value. So load word T1 size also can. Okay, and then this time I can just do the add. Okay, T1. Okay, T1. And then this one is register T1. And then the result will be stored back into T1. And then maybe store after the value of X. Okay, so the next offset of X. So that's it for the first one. Okay, the second one is that if you want to specify the constant, we use a register and then load constant 0. So in this case, if you are writing like this, a sum is equal to 0, like that, right? So if you want to initialize or using a constant 0, or maybe like this, if x is more than register 0. Right. So the coding can be written as, let me make it bigger lah. Okay. So for sum, let's say integer sum is equal to 0. So you can also use or right, immediate kat sini lah. Okay, write it here. It's equivalent to or immediate register T0, register 0, and then 0. So here you can say T0 is equal to 0, like that. Okay, because you all the content inside register 0 with 0. So it means all 0 or 0 is all 0. Okay, so that's how you want to initialize to put a constant 0 in the register. Okay, so using register 0 that load constant 0, and then another way of specifying constant is also using immediate value. For example, using or immediate to say to put x is equal to 1. So integer x is equal to 1 is also can be represented by or immediate P0 register 0 and then 1. So here you are saying 1 or with or 0. So if there is bit 1, then you will get 1. It is T0 will get 1. So this is also using immediate. Sometimes you can also use at I. Just use at I and then T0, register 0 and then 1. This is also the same. You are saying T0 is equal to 0 plus 1 is equal to 1. Like that. Okay, so you can just use immediate value. Okay, and then to add it back, okay, to store it back to the registers. So this is what we call as initialization or specifying constant in the MIPS program. Okay, like you can do it in the middle of the programs. Okay, for example, A more than 5, right? So means that you have to, okay, let's say you want to write that coding. Okay, let's say you want to write that coding. Okay, so we want to write A is more than 5, right? Like that. So what is A? What is A? So A is this one lah. A is this one. A is this one. So first is that what you do is load load address. Kenapa dia naik atas? Okay. Load address and then register as 0, comma A. And then load word. Sorry. Register T0 and then you want to load S0, register S0 like that. So now T0 contain A, which is 1. And then you want to test if A, the content inside A, if the value of A is more than 5. If 1 is more than 5, like that, right? So we want to check. Okay, go back to the lab module. Sorry, not the lab module, green sheet. Green sheet. So which one we need to test? Okay. So if it's more than 5, okay. So branching, we use the branch actually. So you want to test or maybe set less than. Here you can use this sign extend. Set less than. Okay, set less than immediate. So if you want to use it like that, so we can use the command set less than. Okay, so you can say set less than immediate. Okay, but this one is A is more than 5, right? So you can switch the position. So put a command set less than immediate like that. Okay. Okay, set less than, okay, between, okay, 5 is less than A. Sorry, set less than A, like that. Okay, because of set less than means that A is less than 5. So we switch the position. So you can write it like this. Okay, so first is that where do you want to store the 5? So you can put it or immediate like that. and then register T1, and then register 0, 5, like that. Then you can use set less than T0, comma, no, the result should be put in T2. Okay, so T0, and then comma, register T1. Okay, so here it says that, okay, it says that if, okay, if A, okay, is T0. No. Terbalik. T1 here, T0 here. Okay, so is 5 is less than A. And if it's true, it will say T2 is equal to 1. If it's false, T2 is equal to 0. Like that. Okay, so this is for testing that if A is more than 5. Okay, but if it's A is less than 5, if it's A less than 5, then you can put or immediate T1 0 5, and then you can change the position. T0 here, T1 here. So then you can change set less than A is less than 5. Okay, or you can also, no need to use the or immediate, you can just use set less than immediate. This time you can just use the immediate and then put a 5 there. Okay, put a 5. So if A is less than 5, okay, so A is in T0. T0, is it less than 5? Immediate 5. And then if it's true, then save 1 on T2. If it's false, save 0 in T2. Like that. Okay, so that's how you want to how to use the immediate values. Okay, to compare. One is to compare, one is for initialization. Right. So next is the arithmetic operation. So for the arithmetic operation, we have add and subtraction operation. So the last time for the lab assessment 9, right, I asked you to do some addition because you want to add your saving. So when you do adding your saving, it's like you do an addition operation. Okay, so previously when we do the addition, I did not explain it to you that we have a variant of operation in arithmetic. So we have two types or two kinds. One is a signed arithmetic and then one is unsigned arithmetic. So sign means that, okay, sign means, okay, if a sign means that the, let's say T0, okay, contain, okay, 0, 0, 0, 0, and then 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. 1, 1, 1, 1. Like that. Okay, so if it's treated as sign, okay, so sign, so means that this is a positive number. Okay, so this is a positive number. If it's unsigned, okay, so if it's unsigned, this is considered a value. So if you play around, for example, 1 0 0 1 0 0 1 0 0 something 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 1 1 1 0, like that. So 1 here, if it's a sign, means that this is a negative number. But if it's unsigned, this one is considered a value. Okay, so there are different things. Okay, if it's a sign, they treat it as a, considered as a sign. So they will consider it as a 2's complement. So the execution of the instruction may generate an overflow. For unsigned, okay, unsigned, all this overflow. Okay, so when you try to add, so 1 0 0, sorry, We try to add 1110 and then 1110 like that. So you try to add, so 2 and then this is 3 and then this is 3, 1, carry forward, right? So do we need to add or do we need to drop? Okay, so this would create an overflow. Okay, it would create an overflow. So the extra bit there would generate an overflow. So if there is an overflow error, okay, whereby it would stop the coding. Okay, it will stop the coding because there's a trap there. Okay, so in order to bypass the trap, then they use the unsigned. Okay, the mnemonic of U at the end of the command. For example, ADDU, add unsigned, add immediate unsigned. So unsigned here means that they want to bypass the overflow error. Okay, so that they would consider all the bits as the value. Alright. ADD use an R format. So for example, ADD T0, T1, T2 means that T0 is equal to T1 plus T2. If the addition results in 2's complement overflow, the RD remains unchanged. Means that if it's 0, then it's all 0. Because of there's an integer overflow exception trap that would occur. Okay, so a trap is an interruption in the normal machine cycle. So they would trap you, they stop it until we resolve the trap, until we resolve the exception. Okay, so if overflow does not exist, then the result will be placed into RD. Okay, so another form of add operation is ADDI using the immediate. So many of the MIPS arithmetical and logical operations have an alternative form that uses a 16-bit immediate in place of RT. So the immediate value is first sign extended or 0 extended to 32 bits. Okay, means that bukan ini, sorry. Means that if your 16-bit, okay, means like this, If you write ADDI like this and then register T0, register 0, comma 16. So the content inside T0 would become a 16-bit. Okay, so 0, 0, 0, 0, 0, 0, 0, 0. And then 0, 0, 0, 1. Then 0, 0, 0, 0. Like that, right? So that is for a positive number. Okay, because of this is considered as a positive. But if you write it as ADDI, register T0, and then register 0, and then negative 16. Okay, so it would be written, okay, sorry. It will be written something like this. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, 0. Okay, so to represent the negative number. And then when we do the data path, the content of this immediate, would be sign extend to become a 32-bit. So to become a 32-bit, they follow the most significant bit here. Okay, so it will be extended to 32-bit. So they will add. Okay, they will add until it complete 32 bits. So based on the most significant bit, then they will add 0, 0, 0, 0. But if in the case that it is a negative, so the most significant bit is bit 1, then they will extend 1, 1, 1, 1, 1, 1, 1, 1 until they complete a 32 bits of a negative number. Okay, so where do I go? Ni lembut. Okay, so that's why we call that immediate here is a sign. Okay, it's a sign value. So they would sign extend. Okay, so using I or immediate means that you need to use the I format. So 16-bit sign immediate is added to the 32-bit value in RS to produce the result. Okay, so if overflow does not exist, then the result will be placed in RT, the register target. Okay, for example, let's say you write ADD T0, T1 and then 15. So it means that, not 15, it should be 17. ADD T0, T0, 17 means that you want to add T0 plus 17 and then store it back to T0. Okay, if there is no overflow. Okay, if there is no overflow. Okay, so sub. Okay, sub also compute. Okay, means that you subtract and the value between the compute the difference for two sign values. Okay, using a sub means that they consider the content inside the register of RS and RT is sign values. Okay, so this instruction subtract the content of source 2 from the source 1, or it can subtract the contents of the immediate from the source 1 value. Subtract puts the result into the destination register if there is no overflow. So when the true result sign differs from the destination register sign, then there is a signal trap. Okay. So let's say you are writing it like SUB sub T0, T1 and then T2. It means that T0 is equal to T1 subtract with T2. Okay. So adding the two's complement is equivalent to subtraction. So that's why there is no sub. Mana pergi? So there is no sub immediate, but instead of we use ADDI. Okay, that's why when I draw this, remember when I said ADDI can use to represent a positive number and also a negative number. So this is also to represent a sub immediate. Okay, register T0, register 0 and then 16. Okay, so but instead of the 16 here is in a positive number, but this one it can be represented in a negative number. So this is a redundant. That's why there is no instruction for sub immediate. Subtract immediate, there's no subtract immediate. So as you can see on the table, a summary of add and subtract operation is depicted in this table. We have ADD, whereby RD is equal to RS plus RT. Okay, based on this position. And this is a two's complement number, so they can generate a trap. ADDI also the same. They can accept RS plus or maybe subtract. Okay, with immediate, for example, 10. So here is ADDI, RD, RS, and then 10. And then if you want to do some subtraction, then you can put a negative number there. Okay, so this operation would generate a trap if there is an overflow. Okay, ADDIU is the same as ADDI, but instead they are using unsigned. If there is a word or alphabet of U there, it means that okay, the most significant bit, okay, the most significant bit here, this one is considered as a value. So when they do some operation, they would ignore the error. They would ignore the errors because there is no trap. Okay, the same also happen for ADDU. Okay, so this would require two registers RS and RT to be added to the RD. Okay, sub. Okay, sub. If we put a position, okay, if you write the position, okay, if you write sub and then T0, T1, and then T2, like that, it means you are saying T0 is equal to T1 minus T2. Not, okay, this one is correct, but not if you write it like this, if you assume that T0 is equal to T2 minus T1, this is wrong. It's because of the position. Okay, it's because of the position here. The first operand is the RS. The second operand is the RS. The third operand is the RT. So it's always write as RS minus RT. Okay. So if you are using a sub, there is a trap. if you are using a sub U, there is no trap. Okay, so if there is an overflow, then they would generate a trap there. Right, so example of 10.1, write the following instruction in SPIM and see the output. When you want to demonstrate an addition, you need an initialization. So you need to initialize. So remember when I said there are two types or three types of initialization. One is using the dot data. Hilang. Ni dot data. Okay, and then you use the load word, right? And then another is to use or immediate. Okay, so you can also use or immediate, and then register T0, comma, register 0, and then 1. So this is to say that T0 is equal to 1, like that. Okay, same as this one, variable A. So also you can also use the or immediate. So in this case, they are using T1 and T2 to store two values. Okay, and then we add using the ADDU instruction. Okay, so the question is that our register T1 and T2 would change by the ADDU instruction in this program. Okay, in this case, what they want is the value inside the T1 and then T2 and then store it back to T3. Okay, so question asks, does T1 and T2 change value? In this case, the only registers that change is only T3. Okay, because we don't manipulate the data in T2 and T1. We don't store back. Okay, we only store on another register. So the answer is no changes on T1 and T2, except unless one of the source operand become the destination register. So, for example, if you write it like this, and so our immediate T1, you initialize AB. T2, you would initialize 55. And then when I run the coding, so, ni apa nama dia ni ya? Shift So, open. Dah sudah. Abot sekejap. Oh, I missed out this part. Sorry. Okay, sekejap. Hold on. Okay, so now when I want to run or immediate here, so as you can see, okay, so the value of AB is input to T1, and then when I press step again, so 55 will be added to T2, and then when I press again, then ADDU would add the content inside T1 and T2 and store the result to T3. So does any changes happen to T1 and T2? No. Unless you write it like this. T2, T2, T1. Okay. So which register would change? So you can guess it. There. Before this T2 contain 55. Now when I do the operation ADDU T2, T2, T1 means that changes happen on T2 back again. Okay. So that's the answer for the example 10.1. Okay. Remember, sometimes we are not only dealing a positive number, we also deal with a negative number. So, there are another way on how to represent a negative number in 2's complement. Okay. First is that we load the positive number to a register. For example, or immediate T1 082. So now we put 82 into T1 and then negate. Okay, negate this positive number to a 2's complement form. Okay, so to negate it, use the NOR. Okay, NOR instruction, NOR T1, T1, 0. So previously T1 contained 82. Now we complement it using a first complement, okay, command, which is NOR. NOR would change the positive number to become a first complement number. Okay, and then we don't want it to become a first complement. We want it to become two's complement. So we add 1 to T1. First or immediate 1. Okay, so like initialize 1 to another register, which is in this case T2. And then you add the first complement of 82 with 1. Then you will get 2's complement for that number. Okay, so when you add 1, then you will get 2's complement of negative 82. Okay, so so this is the full command, the full programs. Okay, so here is an example that demonstrate the subtract operation. Okay, so in 2's complement negative, this program would add positive 146 to negative 82, leaving the result in T3. Okay, so this is the main example. First is that or immediate, a positive number, and then another positive number 82. So in this case, the second operand or the second operand must become a negative number. So first is that we negate it. Okay, change it to first complement on T1, and then 2's complement by adding 1. So first assign 1 to another register, and then just add. Okay, the negative or the first complement with 1, and then store it back to T1. So now T1 would become a negative 82 in 2's complement. Then you can add 146, okay, which is in T0 with negative 82, which is in T1, and store it in T3. Okay. But there's another way of rewriting the program using ADDIU and store the result in T3. So let's say previously we need a 6 command. But using the ADDIU, you only need to write 2 commands. First, or immediate, T00146. So in this case, you would initialize positive 146 to T0 and then add a negative 82. So remember, ADDI can also store negative numbers, right? So negative 82 and then add with T0, then the result will be written in T3. So these 2 commands will give the same output as the previous one. Okay. So I'm sure that you would prefer to use this one compared to this one, right? But you need to know about this because sometimes when you try to represent numbers, when you want to try to represent numbers, then you need to learn how to use the negation. Okay, the negation command. Right. Next is that we want to start with the operation. Let's say f is equal to g plus h and then I plus 10. So the command is that we start with g plus h. Okay, so in this case, g is S1, h is S2, right? So S1 plus S2 is saved to a temporary register T0. And then I plus 10. Okay, because this is in a bracket, then we prioritize the bracket first. So we prioritize the bracket first. Then S3, ADDI with immediate 10. And then store it in temporary 1, T1. And then lastly, we do the last operation, which is subtraction. So sub U, T0 and T1, and then store it back to S0. Okay. So that's how you want to do that. Okay, so for the multiplication and division. Okay, so multiplication and division operation. Multiplication and division may generate results that are larger than 32 bits. So previously, let's start with numbers. Okay, let's start with numbers. So or immediate, and then so this is for addition. And if you want to write subtraction, you can also just write sub like that. Okay, so the sum is in T3 like that. So you can also use this kind of thing. Okay, so now go to the next instruction operation, which is the multiplication. So multiplication and division may generate results that are larger than 32 bits. So the architecture would provide two special 32-bit registers that are the destination of multiplication and division instruction. In this case, when they do the multiplication and division, actually they are doing it in a binary numbers. So for multiplication, example 1001 multiply by 1111. Okay, if we compare with the addition 1001 1111 like that, if you add, you only add the increment, the size of the result, they only increase 1 or 2 bit. Okay, so like this. Okay, so we just, when we try to add 4 bits, so the increment is only in 1 bit or maybe 2 bits. So the size only increase. Okay, so the source is 4 bit, the result become 5 bits. But if you do the multiplication, so it will become like this. And then when you try to add it, 1, 2, 2, 2. And then when you calculate the bit, how many bits it is 1, 2, 3, 4, 5, 6, 7, 8. So the size of the source is the size of the data inside the source register is 4 bits, right? But when we multiply, okay, it doubles the size. It doubles the size to become 8 bits. Okay, so when if you can imagine, if the source is 32 bits and then your source can become 64 bits. So where do we want to store the result if it's exceed to 64 bits? Okay, so if it exceed more than 32 bits until to the 64 bits. So how do we want to store the result? Because you know the size of the register is in 32 bits registers. So what they do is that the architecture provide two special 32-bit registers that are used to store the destination for multiplication and division instruction. These registers are called high and low. So in the QT SPIM, you can see under the status there is two registers that call high and low. So this is the two special registers that to indicate that they hold the higher 32 bits of the result and lower 32 bits respectively. Okay. So higher let's say we have this is a 32 bit and then this is a 32 bit of the result So the lower 32 bits will be stored into the low register. The higher 32 bits will be stored into high register. Okay, so and then this is only to hold it temporarily. So now you need to move. Okay, so special instructions are also provided to move the data from this high and low into the general purpose registers, which is register 0 and 31. Because of after you do the multiplication or maybe the division, you might need that result to do something else. Okay, so this high and low cannot be used as any operation. They only can be used to store the result. Okay, so next is that, let's say the result must be moved to another register. So we can use move from high to certain registers. Move from low to certain registers. Okay, so we use MF high, MF low. Okay, so this command can be seen on the right panel. Okay, on the right column. Then move from high. So means that the content on high will be stored into RD. And then move from low means that the content in low would be moved to RD. Okay, so this is an R format. So it would use a function 10 for MF high and then function 12 hex for MF low. Okay, so two kinds of instruction are included in the instruction set to do integer multiplication and division. They are sign and arithmetic. So look at the division. Divide here. Can you see divide and also divide unsigned? So they can operate using a sign and unsigned numbers. Also the same for multiplication, multiply and multiply unsigned. M-U-L-T-U. Okay, so if you are using unsigned, the letter U there, so it will never generate an overflow error even if there is an actual overflow. In the case of division, okay. So for the multiplication, okay, the actual MIPS instruction is multiplication RS RT, which means to multiply the contents of RS by the contents of RT. Okay, so if we write it, you want to multiply this, so this will become RS, this will become RT. And then when you want to write it into a coding, okay, you will write multiply RS, RT there. Okay, so where does the result would move? They would move to high, low. And then RS, RT. Okay, how to know that? Here, see? On the logic operation here, RS multiplied by RT, the result will be moved to high, low. Okay, high, low, or not high or low, sorry. High, low, like that. So how do I want to move this result to a general purpose register? So I would use MF high, okay, to register RD, like that, and then MF low to register RD. Okay, so you would need 1, 2, and then 3 command to do a multiplication operation. Okay, so similarly, okay, there is a division for RD, RS, and RT. So actually, there sometimes student can sometimes write a multiplication RD, RS, and RT, MUL, RD, RS, and RT. But the command would assemble the real instruction into 2 commands. Okay, so let's say if you write the instruction of MUL T4, T4, T1, it means you multiply T4 with T1 and then the result would be move low to T4. Okay, why? Okay, why? So if the result is too small, okay, if the result is too small, only the 32 would, the lower 32 bit would have a value. Okay, will have a value. And then high sometimes doesn't have a value. Sometimes they would just get a 0. Okay, if the source value contain a small bits, okay, contains small bits, right? So usually if we do it like this, multiplication RD, RS, and RT, so basically what they do is that they will move flow to the register destination. Okay. Similarly, there is a division RD, RS, and RT pseudo instruction which would do the integer division. This one a little bit different. It's because of they would store different effect. Okay, they would store a different effect. For example, if I write 10 divided by 3, so what I get is 3 times 3 is 9. The remainder is 1, right? So 1 is the quotient, would be stored to low. And then 1 here is the remainder, which would be stored to high. Let me check back again. Betul tak? Okay. Move from high. Okay. Would store, high contain the remainder. High would contain the remainder. Then we can move the remainder to RS. And then quotient contain inside the low. So low can be moved to the RS also. Okay. So now let's do some exercise. You can use this, or maybe we can just use any command. In this case, ori here, don't put 10. Let's put 10. And then this one, T2 contain, asal lah kat situ 10. Hold on. 10. And then this one is 3, ya. 3. Okay. Now put 3 into T2. Now, we want to do a multiplication. Multiplication. So to do the multiplication, this one you can write high, low is equal to 10 times 3 lah. Macam tu. So now, where should I move my high and low? So I would write move from low. The low is the most important. The low is the most important. So register T3 would store the low result. Okay, the low 32-bit result. Here I would write low contain the 10 multiplied by 3, and then move from high. Just use T4. Okay, to store high is equal to 10 multiplied by 3. Okay, now let's save it. Run the coding. So F10. Okay. Let's use decimal. Let's use decimal. Okay, now. T1 contain 10. T2 contain 3. So when I want to multiply F10, so 10 multiplied by 3, you should get 30, which is 30 is quite small, less than 32 bits. So in binary, see that. So the value is in 11110. So it's quite small. That's why it is situated into the low register. Okay. So now 30 is in low. So when I move it, so I would move low to register T3. So T3 would contain 30. And then F10 again. High would move 0 to register 12, which is T4, contain 0. Okay. So that's how you do the multiplication. Okay. But what about division? So if I write DIV. Okay. So now I want to divide 10 divided by 3. Okay. So my low would store 10 divided by 3, means that the quotient. Okay. And then high would contain the remainder. So remainder means we use the percentage equal to remainder, like that. So when I save it, open. Okay, now I have 10 and 3. Now I want to do the division. Okay, now where is the where is the remainder? My mistake. Why did I use the unsigned? Cheat. Okay, now. Sorry. Should be division je. Sorry. Again. Okay. Then, okay, oh, my mistake. This is not 10. T1 is 10. T2 is 3. So, when I want to divide, I should write T1 first. then T2. I see, man. T1 first, then T2. Okay. So then I can just use the unsigned. Okay, doesn't matter actually. So my mistake. Okay, now the position must be in the first one become the value and then this one is become the divisor. Okay, so the second one become the divisor. So T1 divide by T2. So 10 divide by 3. Then I should get the quotient is equal to 3. Remainder is 1. So now again, okay, right. Okay, now I would divide register T1, which is 10, divide by 3. So now my result will be this one. My quotient is 3. My remainder is 1. So when I move again, so I would move the quotient to T3, which is 3. And then the remainder is 1 in T4. So that's how I want to use the division. Okay. So, this is how it looks like in C operation. For division, the symbol is using this one. And then for the remainder, so we will start to B, right? So we will use the percentage, okay, to show to get the result as a remainder. Okay. Now, bitwise operation. So in previous sections, memory access and arithmetic operation view contents of register as a single quantity. Okay, let's say if you want to store T0, 0, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. Like this, Okay, so when we do the load word, we do the add operation, we treat this as value. Okay, like a single entity. We call it as a single value of a single entity. Because it consists of, we need all this bit to calculate the value, right? To get the exact value. But we also can view this register as a 32-bit raw bits rather than a single 32-bit number. So you can treat each of these bits as a number also, as a binary bits, So when we treat it as a raw bit, then we can do several operation of bitwise instruction, such as we want to insert or maybe we want to extract a certain bits, right? So we use like a shift instruction or maybe bit by bit and or not. Okay, we have done the NOR instruction previously to do the negation, right? But this time we are going to learn more about the bitwise manipulation. In this case, shift left, shift right, and then AND logical operation and OR logical operation. Okay, so this is in C++ punya, this is in C++ operators representation. But in MIPS, they are represent using this instruction, SLL for shift left, SRL for shift right, and then ampersand here for operation AND or maybe AND immediate. And then this piping here is for OR logical operation or maybe OR immediate. And then exclamation mark for NOR or NOT. Okay, but in MIPS, we don't have command NOT, but we have NOR command. Okay. Sorry. Aduh, banyak yang ini. Sorry. Alright. So shift operation, there are 3 basic shift instruction. We have shift left logical. Okay, so if it's a shift left logical, for example, we want to shift the bits by 8 bits. So I'll give an example. Let's say I want to shift 8 bits. I want to shift this value by 8 bits. So 8 bits means that you move, okay, the dot, move the dot. So by 8 times. 1, 2, 3, 4, 5, 6, 7, 8. That kind of thing. So you calculate 8 position. So this one here would place here after that. 1, 0, 0, 0. And then just follow this. Just follow. 0, 1, 1, 0. And then just follow this. 0, 0, 0, 0. And then 0, 0, 0, 0. 1, 2, 3, 4. And then 1, 2, 3, 4. 1, 2, 3, 4. So what happened to this part? They would disappear because they are replaced by this number. Okay, they are replaced by this number. So this is what we call as shift left. Okay, so they will remove the left side. And then what about this right side? What happened is that they will just add all 0. Okay. What about shift right logical? So shift right logical means that they will shift to the right, and then the empty bits on the left side will be added with 0. Okay. For example, let's say, mana pen aku ni? Where's my pen? Okay, this is my pen. Okay, example, T0 contain 0, 1, 1, 0, 0, 0, 0, 0, 0, 0, 1, like this. And then you want it to shift to the right. Okay, you want to shift it to the right. Okay, on this side, So what happened is that you shift it 8 bits. So what it becomes is that this will become 1, 0, 0, 0. And then 0, 1, 1, 0. So what happened to the left side? They will just add all 0. Okay, they would add it to all 0. So what happened to this right side here? What happened to the right side? They would be erased and replaced with this value on the left side. Okay, so that is for shift right logical. Okay, let's say you are using SRA, shift right arithmetic. Do we have shift right arithmetic? Tak ada. What is the shift right arithmetic? Shift. This one. Shift right arithmetic, So shift right arithmetic, kenapa dia turun bawah? Why is it going up? Oh, okay. Okay, so shift right arithmetic would fill empty bit by sign extending. For example, okay, if we shift right arithmetic by 8 bits and then the left most significant bit here is 0, then they would sign extend with 0. But if we shift right by 8 bits and then it contain negative sign bit, then they would sign extend with that bit 1, 1, 1, 1, 1. Okay, so that is shift right arithmetic. Okay, so how to do the example? How to see the differences in the shift right logical and shift left logical here? Okay, copy this command, copy this program, and then this one, So and then I will save it. Okay. So the first one, they would add 1 to register 3, and then they would shift the bit by 1 bit, 2 bits, 3 bits, 4 bits, and 5 bits. Okay. You would see that when they shift to the left, the value increase by power of 2. Okay. So 1 means 2 power of 0, 2 means 2 power of 1, 4 is 2 power of 2, 8 means 2 power of 3. It means that you multiply it by bits. Actually, you are multiplying it by bits. 1 multiplied by 2, 2 multiplied by 2 multiplied by 2, you get 4. 4 multiplied by 2, you get 8. And then 8 multiplied by 2 is 16. 16 multiplied by 2 is 32. Like that. Okay. But if you are using a shift right logical, let's say your value is 15. When you shift right, actually it will reduce your bits. Okay, what you will get is that 7, 3, 1, 0, as if you are dividing your numbers. So 15 by 2 is 7. 7 divided by 2 is 3. And then 3 divided by 2 is 1. And then 1 divided by 2 is 0. Okay, so we can also represent the operation of multiplication and division using a shift command. Okay, so now I'm copying it and then I run the coding. Mana tadi? Open. And my shift. Okay, now ADDI register 3 is in V1. Okay, the initial value is 1. The initial value is 1. And then when I shift again, so my T2. T2 is in register 10. T2 is register 10, contain 2. And then 4. So means that we shift 2 bits. Shift 3 bits, you will get 8. Shift 4 bits, you will get 16. Shift 5 bit, you will get 32. Now, let's change the value on register 3 to 15. So, means 15 is all 1, all 1. So, here, change it to binary, If you change it to binary, you will see, okay, in register 3, it contain 1, 1, 1, 1. So, when you shift to the right, okay, shift to the right, okay, 1, 1, 1, 1. When you shift 1 bit to the right, then it will become 1, 1, 1. And then when you shift 2 bits, so it will become 1, 1. And then meaning that they reduce it, They reduce it. So let's sidestep. And then you see, okay, register T7 contain 3 bit 1. And then S0 contain 2 bit 1. And then S1 contain 1 bit 1 here. And then when you step again, you will see S2 contains 0. So you can see that we can represent the shift left as the multiplying, shift right as the division. Okay. So next is the logical operation. Okay, we have 2 basic MIPS instruction. One is AND and then one is OR. Okay, so the meaning of AND is also can be seen in the example of 10, 11. AND can have R format and I format. Okay, I format is the command of NI and also OR immediate. Okay, so logical operation can be both R format and I format. Right. So, for example, for 10.11 here, if T1 contain 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 0. Okay, so let's copy this part, And then, this one. Now, T1 contain 0, 0, 1, 0, 1, 1, 0, 0. Masalah tulisan tak cantik ni. T2 contain 0, 0, 0, 0, 1, 0, 1, 0. Now, okay, let's say we want to AND it. You want to use the AND operation. So, if you are using AND operation, this will become 0, 0, 0, 1, 0, 1, 0, 0. But if you are using OR operation, okay, if you are using an OR operation, this will become 0, 1, 1, 1, 0, 1, 0, 0. So different, right? Different value if you are using AND and also OR. Okay. AND is to compare, or sometimes to use as sometimes can be used for addition or initialization. Okay, so there's a difference of the final content of the registered definition if you are using a different logical operation. Okay, so that's it. But this one is to the complicated one when we want to move the position from 0 to 3 and then from 91 to 29 to 31. But a little bit error there. So I didn't manage to check back the answer for that. So we scrap that coding. Okay, we will scrap that coding. So that's it. Now it's 12:25. Okay, 12:25, and then you still have a time to do the exercises. So for example, I can just check for your coding for question, self-review question here. Try to write the program that adds up the following integers. And then leave the answer in register 8. I want to see how do you want to write it. If you want to write on a piece of paper also can. If you want to write on a notepad also can. And then I'll give you until 12:50. Okay, 12:50 to finish the, for me to check your answer. And then we can end the session. Okay, so try to answer for the question 1, question 2, and then question 3 would be your lab assessment. Okay, so just write anything that you want. I'll just check your answer. Okay, so chop, please do it now. Oh, Fong asked question. Sorry. Madam, for or immediate T1082, can I write in load word? T182. Yeah, we can try. I think it can work. Let's open. Let's open. Apa saya tak buka ni? Ni. Let's open the test. Load word 82 Okay, load word 82. ADDI T0 T1 and then T0, so maybe 104 like that. And then I close it. Okay. And then I will save it there. So let's try. I think it can work. Actually, it can work. But I'm not sure if it's error or not. Oh, boleh pula. Tak jalan. Kenapa? Salah. Sorry. Tak boleh. Because they would treat it as an offset. It would treat it as an offset. It would treat as an offset. So the result will become 0 nanti. It bukan 0. Not 0. It will be different. There. Exception. Okay, so there's an exception there. Cannot. If you want, just use the or immediate. Sorry. Let me share. Sorry. I'm just talking to myself. Right. Fong, you asked if we can use the load word. Load word means you want to load the content on the address. So when I write load word T0 and then 82 and then just test it with ADDI. So what happened is that when I run the command, okay, test, and then when open, okay, what happened is that the load word for 82 becomes an offset. They become an offset there. You see? And then the register bit is register 0. So when I run the coding, they give you an exception occurred there. Okay, they would abort. Okay, so cannot use the load word lah. Load address is for memory address only. But you can use the what else we can use the load word, load apa immediate. No, you cannot. Load immediate. You can use the load immediate, I think. Load immediate. Load immediate. You can use the command load immediate. I remember that I did use the load immediate. And then when I test it, there. Load immediate T082 becomes or immediate. Still give you answer. It will still give you answer. Change it to decimal lah. There. So there. Now it can run. So if you want to load a value, use load immediate. If you want to load the content on a certain address, then use load word and load address. There's a difference there. Okay. So please continue the exercise that I have given you. Okay, Fong, understand that, right?
Yes, madam.
Okay. Okay, you're done? You're done?
Done.
Okay, please show on
I
the
already sent it in WhatsApp.
WhatsApp. Kejap. Hold on. Laju aja semua untuk WhatsApp ni. Tunggu. Hold on. My PC is slow. Today is supposed to be a face-to-face, and then there's something happened to the faculty. So that's the reason we are doing the. Okay, T00456, and then you use add IU, and then add I, and then add IU negative. Okay, all right, and then there's another one, I think. Oh, only 1%. This one is not. Bukan. Only may you send the answer? Let me check. Others doesn't have answer? Tadi. So, let me share. Ni. Have you tested this, Mayo? Oh, already. Negative 229, 325, and negative 552. All right. So only one who sent the answer. So that's it, right? So okay, that's all. Okay, I'll see you next week. Next week we will do a program sample. I think how many types, huh? Mana pergi? This one. Okay, it's a translating. Okay, using an input output. Okay, using a C in C out, and then if then else. We have if then else. What else? Branching, branching, and loop instruction. Okay, I will teach you about the loop instruction for and also lastly array. Okay, array for next week. If we not be able to finish it, then we can just continue the next one. Okay, so that is for next week. So for the lab assessment, I want you to do the question 2 and also question 3. Okay, so last time you learned how to use the load word, and then load up immediate and everything, right? Using the dot data. So I want you to combine what you have learned so far. Okay, and then this week and last week, and then answer the question for question 3. So question 3 can use the load word. Question 2 is only for shifting. Use only a bit pattern. So you can just use the shifting, shift right, shift left, and everything else. So you can try to answer for the question 2. Okay, so that's all. Question 2 is for your project, actually. A little bit for your project. Okay, so that's all. I'll leave it up to you to answer the question later on. So we will end the session today. I'll see you next week. So that's all. Bye-bye. Assalamualaikum.
Thank you, madam.
Welcome.
Thank you, madam.
Thank you, madam.